So far, we've been talking about probability theory. I've also mentioned to you that the field of statistics builds on probability theory in order to make inferences about the future or in order to quantify our certainty about events. So let's start to examine that now. So the field of statistics applies probability theory to make inferences with a quantifiable degree of confidence. So for example, let's say we ran a 5 coin flip experiment 1,000 times with a fair coin. So I'm adding another argument in here to the binomial method that we've already been calling. So we're going to do experiments that each have 5 coin flips in them. We're still going to have a fair coin, so it's going to be heads 50% of the time. And now we have this additional argument, which is a number of separate 5 coin flip experiments. So let's say that we're going to do 1,000. That seems like a pretty big number. So now with our specific number of experiments, let's run the 1,000 experiments, and we'll collect our results in this heads count variable. So we can plot the results of our experiments to create a probability distribution. We are going to be talking about probability distributions a lot in these live lessons, and this is our first introduction to them. Okay, so we'll use this line of code here to count up the number of experiments where we rolled no heads, where we rolled 1 head, where we rolled heads twice, and so on. And so this first array, this first vector, tells us, okay, this corresponds to the number of experiments in which we had no heads out of the 1,000 that we ran. And this event count variable gives us the corresponding number. So out of 1,000 experiments, there were 33 in which we rolled no heads. There were 181 where we rolled heads once, and so on. So clearly, from examining these numbers, it was a much higher probability of rolling 2 heads or 3 heads than the other values. And the further we get out to the edge, the less likely that outcome is. So it's pretty unlikely that we have 0 heads or 5 heads. And so we can divide these event count numbers by our number of experiments, which is 1,000. And so that gives us the probability of that event occurring. And we can plot that out. So I've got a simple bar chart here, which shows the implied probabilities by the experiment that we ran, or by the 1,000 experiments that we ran, of 5 head flips. And so we're seeing here about a 3% chance of no heads out of 5 tosses, and same thing, about a 3% chance of getting 5 heads out of 5 tosses. So this corresponds very nicely to the 3.1% that we calculated earlier in the final exercise that we did together. So we calculated here in this exercise, based on combinatorics and this coin flip probability function that we created, we determined that there is a 3% probability of getting 0 or 5 heads in a 5-toss experiment. And there was a 16% chance of getting 1 or 4 heads, and a 31% chance of 2 or 3. And so these values, these probabilities that we determined using combinatorics, using factorials, correspond very nicely to the values that we get when we run this simulation. So we're getting very close to the same values, around 3%, 16%, 31%, and so on. And if we increase our number of experiments according to the law of large numbers, so if instead of doing 1,000, you did 10,000 or 100,000 experiments, the more and more in line these probabilities that we get in our simulation would line up to the probabilities that we calculated using combinatorics. So let's say we'd like to now test a coin as to whether it's fair or not. So we flip it 5 times, and all 5 times it comes up heads. Does this imply that it's not a fair coin? Well, statistics arms us with tools to use the probability distribution that we just calculated in the code to answer this question with a particular degree of confidence. Is this coin fair or not?